This is Algebra 2, Lesson 10-6, Points of Discontinuity. Today's date is Wednesday, April 15th, 4/18, 2020. Our objective today is to determine if an x-coordinate is a zero, vertical asymptote, or removable discontinuity, assuming it is some sort of point of discontinuity. Okay, so let's talk about those three different types of discontinuities. So I'm going to go ahead and show you a picture or a graph of what a zero looks like. So say you have some set of axes. So let's do like our x and our y. So this is, you don't have to label them, but x and y, right? A zero means that I'm going to have some sort of function that passes through the x-axis. So this is a zero right here. 0, and this is a 0 right here. Another name for a 0 is an x-intercept. So I'm going to put x-intercept. That's another name for it. So we know how to find those. What about a vertical asymptote? We haven't really seen these too often before. You might have seen it, but I haven't officially labeled it. So again, go ahead and draw some sort of axes here. Let's say we have a function that comes up and then goes up and towards infinity, and then maybe another function that comes up towards infinity and continues elsewhere out here. Actually, I'll do two different types. So I have a vertical asymptote like that, and then I can have one that can come up again, and instead of coming up, I'll come down. Okay, so what are the vertical asymptotes here? I have a vertical asymptote, and usually it's a dashed line right here, a dashed line right there. Those would be the vertical asymptotes. Vertical meaning going up and down, not left or right, right? And then what does a removable discontinuity look like? And I guess I have a line tool. I could be using that. Is this? Okay, well, I haven't set that up yet, so I'm just going to keep drawing like I have been doing. Removable discontinuity is if I have some function that's like a line or a curve, and then I took a hole punch and chunk, that one point doesn't exist, and maybe chunk, that point doesn't exist, but everything else does. I just kind of remove 1 or 2 points depending on how many different removable discontinuities I have. Alright, so that's the picture of what's happening here. What does it look like when I have a rational function? Again, rational meaning some sort of fraction. Whenever I have a zero, that means I have some zero in the top. So I'll say that you're really analyzing the zero that's in the top, and I don't care about what's happening in the bottom, so I'm going to just scribble that out. What about a vertical asymptote? That's where I only care about the zeros that are in the denominator, and I don't really care what's in the top, as long as everything is simplified and you cross out all the things that are common, right? You've reduced our fraction. And the rare type of thing is getting the removable discontinuity where you have a zero both in the numerator and in the denominator with no extras of those zeros. And I'll talk about that, I think, in example 3. And they can cancel each other out. So when they do cancel each other out like this, that is a removable discontinuity at that zero. Let me show you some kind of quick examples what would happen down here for these types of functions. So if I had like x plus 1 all over just 5, that's I guess it's not really a rational function. To make it a true rational function, I could do x, but again, I'm kind of ignoring that bottom part because I only care about the zero that's in the numerator to find a zero. So I'd say that I have a zero here at x is equal to -1. Why -1? Because again, you're setting this this term, this expression, to 0. When you set it to 0, then you're going to subtract 1 from both sides, and you'll get a 0 at x is equal to -1. Of course, you'd have a vertical asymptote down here at x is equal to 0, but I'm going to ignore that just for the sake of that example. What about a vertical asymptote? Let's do another example. What if I had like, I don't know, 5 over x plus 3? Well, then I would have a vertical asymptote at x is equal to -3. Again, you're setting that denominator equal to 0, and that will be your vertical asymptote. And what would be an example of a removable discontinuity? Something like x minus 2 over x minus 2. That would have a removable discontinuity at x is equal to 2, because again, you're setting those equal to each other, and they are the same on the top and the bottom. There's your quick rundown. Let's go ahead and jump into an example. So this is modeled on a Khan Academy problem, so it should be very familiar. once you start doing the homework tomorrow. This is going to be a longer lesson, so okay, so we have some sort of rational expression, numerator and denominator with polynomials, and I need to figure out at 1, -3, and 2, what do I have? Do I have a 0 there, or do I have a vertical asymptote, or do I have a removable discontinuity? One of those needs to be checked. And the key thing here is you can't have both. I can't say it's a 0 and a removable discontinuity. It's one or the other. So in order to solve this problem, I'm going to factor. I have to have a factor of linear factors, I guess. So this is going to be a ninja star. I can do some work off to the side. So my ninja star is going to be a 1, this coefficient 1 in the bottom, and then -6 in the top. For all of today's, or I guess tomorrow's homework and today's lesson, we're only doing normal ninja stars. I don't think we'll ever do an advanced ninja star. So you can keep using this just normal ninja star. So what times what is 6? 1 and 6. Okay, that doesn't get to 1. 2 and 3. Oh yeah, that does get to 1. So 2 and 3, and the 2 has to be a negative. So I factored this as x minus 2 times the quantity of x plus 3. Perfect, we factored the top. Now for the denominator at the bottom. Let's do another ninja star. I'll do this one in red. So advanced ninja star, or normal ninja star, 2 in the bottom, -3 in the top. What times what is 3? 1 and 3. Those are the only factors, and the 1 has to be a negative. So this is going to be x minus 1 times x plus 3. All right, so right away I can see that things are going to start canceling out. So I don't have to list any values that make this expression undefined. I'm kind of skipping that step. Right away I can see that that gets crossed off. Whenever you have something that's crossed off, you should suspect that it's a removable discontinuity, and in this case it is. The only time that it would not be a removable discontinuity is if I had another of these linear factors. If I had another x plus 3 randomly up here, then this would overpower the fact that those are canceled out, and you kind of just cancel them out and then totally ignore them. They don't, like, you don't worry about them at all. But since there's no extra x plus 3 in here, that's just a removable discontinuity whenever I set this equal to 0. So setting this equal to 0, that means at -3 I will have a removable discontinuity. At x is equal to -3, I have a removable discontinuity. And then this is a linear factor that's in the top. Again, if I'm looking at my table up above, whenever I have a 0 in the top, that's going to be a 0. A 0, and the denominator is going to be a vertical asymptote. So this linear factor is going to be a 0. This linear factor is going to give us our vertical asymptote. And sometimes you won't have all of them. This is a case where I showed all three just to test it out. So I'll have a 0 at 2. So at this 2, I'll have a 0. So give a check there. And at 1, I'll have a vertical asymptote. At 1, I'll have a vertical asymptote, and I'm done. Let's do another example. Example number 2. So same type of thing. We're going to ninja star this. Let's ninja star the top. So it's going to be 3 and -10. What times what is 10? 1 and 10. No, 2 and 5. Ooh, that might work. So 2 times 5. Yep, the negative for the 2. And this is going to be x minus 2 times the quantity of x plus 5. What about for the denominator? So that's going to be another ninja star off to the side. 3 in the bottom, 2 in the top. What times what is 2? 1 and 2. Oop, 1 and 2. And 1 plus 2 also add up to 3. So we're good. This is going to be x plus 1 and x plus 2. I'm looking at this problem, and at first it might seem that those can be canceled out, but one is a plus, one is a minus, so nothing can be canceled off, which means we do not have any removable discontinuities. None of these should be checked. Nothing canceled out. So what do I have? In the top, I have x minus 2 set equal to 0. So at x is equal to, this is going to be a positive 2, I'll have a 0. So at positive 2, I have a 0. At negative 5, I also have a 0. At negative 1, I'll do this down here. At negative 1, I have a vertical asymptote. Again, when it's in the denominator, there's a vertical asymptote. And at negative 2, I have a vertical asymptote. And done. And let's try example number 3. It's the trickiest type of problem because it's one of those where it seems like we have a removable discontinuity, but it's not. So What do I mean by that? Let's go ahead and do the same exact steps, factor the numerator. So ninja star is going to be 8 and 16. What times what is 16? Oh, 4 and 4 in this case. 1 and 16 didn't work. 2 and 8 didn't work. Yeah, so 4 and 4, there are only 2 that work. So this is x plus 4 times the quantity of x plus 4. And what about the denominator? We have another ninja star, 3 and negative 4. What times what is 4? 1 and 4. Oh yeah, that works. 1 and 4, where the 1 is negative. So this is going to be x minus 1 and x plus 4. All right, so right away I see, oh yeah, I have 2 of these x plus 4s. So I'm going to cross that one off and cross that one off. And it makes me think that at this x is equal to negative 4, I'll have a removable discontinuity because, look, I removed it, so this should be the answer, right? No, it's not, because I have an additional x plus 4 over here, which overpowers the removable discontinuity. The general rule of thumb is the removable discontinuity is very easily overpowered when I have an extra linear factor either in the numerator or denominator. So I kind of ignore all of that altogether, pretend it wasn't even there, and I just pretend that it was only in the numerator. And again, the numerator gives us things that are zeros. So I have a 0 at negative 4, and I have a vertical asymptote at 1 because that's the denominator. Cool. That was actually a quicker lesson than I thought, but as I don't want to go back on my word, that was our lesson for today. You can go ahead and do the homework right now, but the official homework is going to be starting tomorrow. I'll see you guys later.